To find the prime factors of a 2048-bit number, it would take a classical computer millions of years. A quantum computer could do it in just minutes. And that is because a quantum computer is built on qubits, these devices which take advantage of quantum superposition to reduce the number of steps required to complete the computation. But how do you actually make a qubit in practice? And how do you read and write information on it? I met up with researchers who are using the outermost electron in a phosphorus atom as a qubit. This single phosphorus atom is embedded in a silicon crystal, right next to a tiny transistor. Now the electron has a magnetic dipole called its spin, and it has two orientations, up or down, which are like the classical 1 and 0. Now to differentiate the energy state of the electron when it's in spin up and spin down, you need to apply a strong magnetic field.
And to do that, we use a superconducting magnet. So a superconducting magnet is a large solenoid, is a coil of superconducting wire that sits inside of that vessel that is full of liquid helium.
So now the electron will line up with its spin pointing down. That's its lowest energy state. And it would take some energy to put it into the spin up state. But actually, not that much energy. And if it were at room temperature, the electron would have so much thermal energy that it would be bouncing around from spin up to spin down and back. And so you need to cool down the whole apparatus to only a few hundredths of a degree above absolute zero. That way you know that the electron will definitely be spin down.
There is not enough thermal energy in the surroundings to flip it the other way.
Now, if you want to write information onto the qubit, you can put the electron into the spin-up state by hitting it with a pulse of microwaves. But that pulse needs to be a very specific frequency. And that frequency depends on the magnetic field that the electron is sitting in.
So what you see here is the frequency that is being produced by this microwave source, and it's 45.021 gigahertz, which in the magnetic field that we are applying now is the resonance frequency of the electron.
So the electron is a little bit like a radio that can only tune into one station. And when that station is broadcasting, the electron gets all excited and turns to the spin-up state.
But you can stop at any point. So if you just make it mutate and stop your pulse at some specific point, what you've created is a special quantum superposition of the spin-up and spin-down states with a specific phase between the two superpositions.
And how do you read out the information? Well, you use the transistor that this phosphorus atom is embedded next to.
The spin-down has the lower energy and the spin-up has the higher energy. Now, in this transistor, there is in fact a little puddle of electrons. This puddle of electrons is filled up to a certain energy. So this vertical axis here is energy. And here we have all these electrons that line up in energy just like the electrons on the shells of an atom. So now, if the electron is pointing up, it can jump into the transistor, right? Because it has more energy than all the others. It leaves behind the bare nuclear charge of the phosphorus, right? The phosphorus has one more positive charge in the nucleus as compared to silicon, but normally it's neutralized by the extra electron, so the two things cancel out. But if you take the electron away, then the phosphorus has a positive charge. So it's as if you have a positive voltage, a more positive voltage applied to this gate. It doesn't come from the gate, it comes from the atom, but it's the same. It's just a positive voltage.
It's like the transistor has been switched more on. And so you see a pulse of current, and that indicates that the electron was in the spin-up state.
In this measurement phase, if you find one of these spikes of current, it's because you had an electron spin up. So you can play catching a spin up or a spin down electron. You see there was no current here, that was a spin down electron. You can try again. Again a spin down electron. Spin up electron.
Now these researchers have actually gone further, using the nucleus of the phosphorus atom as a qubit. Like an electron, the nucleus has a spin, although it's 2,000 times weaker than the spin of the electron. But you can still write to it the same way using electromagnetic radiation, only it needs to be a longer wavelength and a longer pulse in order to get the spin to flip.
Because it's so small, so weakly magnetic, and so perfectly isolated from the rest of the world, it's a qubit that lives for a very long time.
But how do you read out the spin of the nucleus? Well, you use the electron. Remember that the electron's frequency that it will respond to depends on the magnetic field that it's sitting in.
So that magnetic field is the external magnetic field that is produced by the superconducting magnet, but there is also an internal magnetic field coming from the nucleus. But that internal magnetic field can have two directions, right? The nucleus can be pointing up or down itself. So what it means is that there are two frequencies at which the electron can respond depending on the direction of the nucleus.
So the nucleus actually acts as a little selector. It tells the electron basically which radio station it can listen to.
So what you're looking at now is an experiment where we actually flip the nucleus every 5 seconds. So for 5 seconds, you will see that the electron always responds because the nucleus is always in the right direction to make the electron respond to the frequency we were applying to the electron. And then for the other 5 seconds, the electron will not respond because we have flipped the nucleus the other way. So now watch, you see?
In this period of time, the nucleus has been flipped down.
Yeah.
And now after 5 seconds, it'll flip up, and
Yeah,
then
you
the
see?
electron starts responding.
Yeah. So you are watching on the oscilloscope screen in real time the measurement of the direction of a single nucleus and our ability to flip it at will every 5
The
seconds.
spin of a single nucleus. Now, because all of this depends so sensitively on magnetic fields, you need to make sure to eliminate all spin from the silicon crystal. But unfortunately, natural silicon contains about 5% the isotope silicon-29, and that does have a spin.
But in fact, the beauty of silicon is that it has this isotope called silicon-28 that has no nuclear spin. The nuclear spin is 0. So it's a completely non-magnetic atom.
But where are you going to find a pure crystal of silicon-28? Oh, wait.
These isotopically purified silicon-28 crystals are being produced anyway for a purpose completely different from quantum computing. They're being produced to redefine the kilogram through the Avogadro project.
So the offcuts from that silicon sphere are actually being used as the home for qubits. Hey there! This episode of Veritasium was supported by Audible.com, a leading provider of audiobooks with over 100,000 titles in fiction, nonfiction, and periodicals. Now I'm heading out today on a road trip across the US, and I am taking with me Nate Silver's book, The Signal and the Noise, Why So Many Predictions Fail But Some Don't. Now if you want to listen to that along with me, you can download it for free by going to audible.com/Veritasium, or you can download any other book you like for free for a trial offer for 1 month. So I want to thank Audible.com for supporting Veritasium, and I want to thank you for watching.